Hi, I'm Paul, and we are doing Leetcode must-know interview questions. Today's challenge is longest increasing subsequence given an integer array nums. Return the length of the longest strictly increasing subsequence. What is a subsequence? Subsequence is an array that can be derived from another array by deleting some or no element without changing the order of the remaining element. I've never really liked that definition that much. It's well. A subsequence is a, I think the key thing is it's the numbers don't have to be consecutive. Okay, so a subsequence, for example, in this one here, example 1, we have 2, 3, 7, 101. The length is 4. It could be 18 as well. You could go 2, 3, 7, 18. So we're looking for numbers that appear in order in the array, but not necessarily consecutively. And what else do we need to know here? It's strictly increasing. So if you just have the same number over and over, that's just a subsequence of length 1. Every element in there is a subsequence of length 1. So it has to be strictly increasing. Length of the nums array can be up to 2,500, and there can be negative numbers even though they aren't in the example, but we're going negative 10,000 to 10,000. All right, so we're going to do a top-down dynamic programming. Oh, you know what? There is one thing at the end of this. Can you come up with an algorithm that runs in n log n time complexity? And the answer is yes, but it's not a dynamic programming algorithm. And this problem is in the dynamic programming category. So we're not going to do the n log n, but you can do it. You can take the array and you can build up a list in making sure that every time you put a number in the list, you're either going to be adding a number to the list or replacing a number in the list, but you're going to be keeping it in sorted order, which is going to allow you to do a binary search to figure out where each number goes. Okay, we're not going to do that. We've done everything so far on dynamic programming in bottom-up fashion, so we can try and do this one top-down. Let's see. Let's look at example 2. Okay, so one way we can do this is we can do it. We can build up a list of the same length as the array, and each number in the list is going to be the length of the longest increasing subsequence ending with the corresponding number. Okay. Now the question is, how do we compute the longest increasing subsequences? Well, we can do it recursively. We can start off, here and say, well, that's 1. It can't be any longer than 1. And then for each number, we look back at previous smaller numbers and figure out which one is the max and just add 1 to it. So this way we can look back and say, all right, there is one smaller number. So if we add 1 to it, it's going to be the longest increasing subsequence we can have here is 2. Okay. Now we go to the next number, 0. Look at the numbers to the left. There are no smaller numbers to the left. So we go to 3. Well, actually, we should put a 1 there because the longest increasing subsequence ending there is 1. We can go to the 3. Let's look at smaller numbers to the left. They're all smaller, and the biggest number that we have there as far as the longest increasing subsequence is 2. So we add 1 to that and we say, all right, so the longest increasing subsequence ending here is going to be 3. 2. Looking to the left, the longest increasing subsequence to the left And we can't count the 3 because 3 is bigger than 2, but we can look at the 1. The 1 has a longest increasing subsequence of 2. So the longest increasing subsequence ending with 2 is going to be 2 plus 1, and that is 3. And finally, we are at 3 here. We look for numbers to the left that are smaller. Which one has the longest increasing subsequence? It would be the 2 right next to it. We add 1, and we get 4. So 0, 1, 2, 3. Output is 4. All right. This is often the way that we start out doing top-down dynamic programming, is start out writing it as a recursive algorithm. All right, so let's try that. All right, let's start out with this. Let's say that int n equals, any spaces there, int n equals nums dot length. Okay, and then, no, we need one more here. Int result equals 1. Can't be less than 1. Can it? Let me look at no, because the array has to have at least one number in it. All right. For int I equals 1, I is less than n, I plus plus. Why are we starting I at 1? Well, we really don't have to look at the first number in the array. That is going to have a longest increasing subsequence of 1. So we really need to look at the second number, which is at index 1, because that could possibly have a maximum increasing subsequence that's longer than the default result. So let's say max equals math.max. What we want to return is either, not max. Result equals math.max of result, which starts out as 1, or we're going to write a recursive routine here. List ending at I. And we'll send in nums, and we'll send in, no, that's right. We'll send in nums, and we'll send in I. And we'll return result. All right, what is happening here? If we have a default of 1, that's the smallest number that we can return, we are going to iterate from 1 to the end of the array and find out for each number in the array what is the, I shouldn't actually call it list. Let's call it longest increasing subsequence ending at I. Okay, so we'll compute that recursively. If I can copy it here. Okay. So here we could say private int longest increasing subsequence ending at I. The input is going to be an integer array. We can call it AR. And for the index, we can call it, I don't want to give it the same name. Let's call it IDX. All right. I'm not sure we need a base case here. If this if this fails for some reason other than a timeout, we'll add a base case. But let's do this. Int max equals 1. And that's just our default. 4. Int previous equals 0. Previous less than index. Now, you see what's being passed in here is going to be initially 1, and then 2, and then 3, and then so on, up to the final number in the array. And so this loop, this for loop here, is going to look at all of the numbers to the left of the number at index, IDX. Okay, let's say max equals math.max. It'll be the max of max, or, let me copy that again. Array dot previous plus 1. Okay, so in here we're getting indexes in here. The index is going to increase every time we call this. Well, yeah. So let's see. We pass it in math max result list ending at I nums I. Right. So every time that we call it from here, I is going to be bigger. So I is going to, let me scoot this over a little bit. You know, as in our example, we are going to examine these numbers from left to right. And here, when we get the numbers in, we are going to examine the numbers to the left of the index. Again, from left to right. Find out what is the maximum longest increasing subsequence that we have for numbers less than the current index. Add 1 to it. If that is greater than max, then we'll set max to the new value. All right. I feel like that is all we need. Okay, we set the n, we set the result, we set the loop. We'll return the result. We have a recursive call to compute. All right. I have a feeling this is not going to run within the time limit. Well, I mean, it'll run when we click run. But when we actually submit it, unknown network error. What does that mean? Am I logged out? Hang on. All right. Looks like I got logged out. Log back in. Let's try and run it. Compile error. Okay, that is line 16. Missing. Oh. What is that? Whoa. Yes, PREV plus. Did I really leave that out? All right, let's try it again. Wrong answer. Hang on. All right. Well, it's possible that I do need a base case here. Usually recursive functions need a base case. I thought in this case it would not go below, it would not go to 0, but maybe it will. Let's try that run and see what happens. Let's bring this up. Still wrong answer. Okay, hang on. Okay, about that. What we need here is if ARR previous is less than ARR index. We'll look at smaller numbers. Whoa. Array index. All right, one more time. Okay. A couple of false starts, but accepted. I'm going to submit this. I would be surprised if it doesn't time out, but we'll see. It's an exponential. Uh-oh, is this actually going to work? An exponential algorithm if we do it this way. Yeah, time limit exceeded. Okay. Here's why this is a bad idea. Can I scroll this up? Okay. So it's a recursive algorithm. So that means, and let's take a smaller number of elements for the array. Let's get a pen here. Let's say we have four. Let's say we have 4 elements in the array. Well, we can tell what the longest increasing subsequence is if we know what is the longest increasing subsequence at index 1, what is the longest increasing subsequence at index 2, it's not a very good 2, and what is the longest increasing subsequence at index 3. Okay. In order to get the longest increasing subsequence at index 2, we have to know the longest increasing subsequence at index 1. To get the longest increasing subsequence at index 3, we need to know the longest increasing subsequence at 1 and 2. This pen is really slow today. 2. Those two twos are equally bad there. Okay, now the problem is we're not remembering any of these computations that we do. So even with a small number like 4, we would have to do the computation for index 2 twice, here and here. Now, the maximum number of elements in the array is 2,500. You can see we timed out here that this array over here is it's pretty big. You know, there's a lot of numbers in it. So now what we do to convert this to dynamic programming is we use something called memoization. We use tabulation for bottom-up dynamic programming. For top-down dynamic programming, we use memoization, which means we notice that we are doing the same computation over and over. So what we have are like overlapping subproblems. Okay, so when we do the computation once, we store it. So then if we come to that computation again, we just look it up. We don't perform the computation again. And that actually speeds things up considerably. So let's try that. And we can modify the code here. Let me scoot this over a little bit more. We can modify the code that we have for the recursive method. All right, so we have recursive calls here. This is what's killing us. Notice that we only have one variable that changes in the recursive calls. That's the previous variable. It runs from 0 to idx, so n minus 1. So we need a one-dimensional array of size n, which we can initialize the values to -1 to indicate that they haven't been updated yet. All right, so we still need that. We need something. You know what? We still need. Let me put it this way. We still need that. We still need that. We need int an int array we'll call memo equals new int of size n. We're going to fill the array with -1. We set for int I equals 1. I is greater than n idx. No, I plus plus math max result. Yes, okay, but we have to do one more thing here. We have to send in the memoization array. Okay. Oh no, I'm already here. Okay. All right, for this, if index equals 0, return 1. I still don't think we need that. If memo idx is not equal to -1, return memo idx. All right, good. If we computed this index before, we're not going to compute it again. We're just going to pull out the memo array. Int max equals 1. We still need that. Oh, wait a minute. I need to add. I need to change the method signature. Int memo. All right. Max is 1. That's good. For int prev 0, prev less than prev plus plus. If array prev is less than, so max equals math.max equals blah blah blah. Again, we have to send in the memo array. Okay. Return max. That is going to be inadequate at this point because we want to memoize it. So we'll say memo array at idx equals max, and then return max. All right. Run it. Accepted. Submit it. Result not supported. Oh, wait a minute. Oh, my God, I thought I was going to time out again. Okay. Let's see what we have here. Runtime. Well, that still is not very good. I mean, you can do this bottom up also. Gee. Well, okay. Let's think about what we're looking at here. There's a big, well, I don't know if it's that big a gap actually. What is this? This is 38 seconds. What did we get? Like 77? Okay. It's still, I think, n squared, right? Complexity analysis, n squared. This one over here may be, if anyone implemented the n log n algorithm, again, though, it's not dynamic processing, so I didn't think it would be that useful. Maybe the bottom up is faster. Okay. I don't have anything. I don't really have anything to add to it. I'm tempted to try the bottom up and see if it comes out faster. But otherwise, that's it. Please feel free to like, subscribe, comment, and see you next time. Okay, so one last thing. I did write it as bottom up and ran it. It is quite a bit faster. So you can see, we're, in the middle of the second group here again. I think this is probably the analog n algorithms. What else? And I also did want to see you. I did want you. I just want you to see what a top-down solution looks like relates to recursive solution, and that it's fairly easy to convert. If you can come up with a recursive solution and notice that you have overlapping subproblems, then it's not hard to convert into a dynamic programming problem. Memoize the solutions. Okay, that's it. Thanks. Okay, actually, I did want to add one more thing to this, and that is the bottom-up solution. The bottom-up solution is very much like the other DP problems that we did with bottom-up solutions. So, a good exercise. Go ahead and try and implement the bottom-up solution. And okay, that's it for real this time.